Hey guys, and welcome to a new video in this computer vision tutorial. In this video here, we're going to do camera calibration in Python. So first of all, we're going to talk about what is camera calibration and why do we need to calibrate our cameras before we're using them in our application. And then at the end here of the video, I'm actually going to show you a script that we can just run in Python on several images that we take with our camera and a chessboard, and then we're going to do camera calibration on that, and we're going to get the camera matrix and also the different kind of distortion parameters and stuff like that from the camera calibration that we're going to do on our camera here, so we can actually remove distortion on our images. But first of all, remember to join the Discord server. I'll link to it down in the description here, and you can join the Discord server and come chat with us about computer vision, artificial intelligence, deep learning, and stuff like that. And also, if you have a project where you're doing some different kind of stuff and you have some problems, you can go ask me a question in there or just come in for inspiration. You can now also become a member of the channel if you hit the blue button under the video here, and then you can support the channel here with a small monthly fee every month, and all of it will go to creating more and better quality content on this channel here. So first of all here, we're going to talk about what is really camera calibration and why do we need camera calibration. So when we're doing camera calibration, we need to use multiple images of a chessboard here in the image where we want to calibrate our camera on. So in the example over here to the right, we can see that when we're calibrating our camera here, then we actually take a picture of the area that we want to have our camera operating in, and then we're going to use this chessboard here where we're going to move this chessboard here around. So we need to have a known object here, and in this case here we're going to use a chessboard, and then we need to have multiple images where this chessboard here is at different positions. So we both need to rotate it around, translate it around here in the image, and also tilt it, so we actually get tilted chessboards with our camera as well, so we can then use that information to actually calibrate our cameras. So as we can see here over to the right, we're actually going to calibrate this camera here, and then we're going to find the corners here of the chessboard. And then because when we know the object in the 3D world coordinate, then we can actually use that information to calibrate our camera and also get our distortion parameters. So down here at the bottom here, this is actually the image that we have undistorted. So we can see that we have some curves here at the end of the table here. So we can see that we have this barrel distortion here in the image up here that we're going to remove by using camera calibration. And then when we actually undistort our image down here at the bottom, then we can see that we just get a straight line here of this table here, where we don't have this barrel distortion or this curve up here. So down here is actually the result of the image when we have calibrated our camera. And when we're going to do operations later on and doing some different kind of stuff for our own application and our own projects, then we will kind of make more accurate calculations and different kind of operations when we actually have these straight lines and we have removed distortion in our images, compared to if we're operating with distorted images up here as well. So we can get more accurate results and do more operations on our images when we have calibrated cameras. So we're going to compute the camera matrix, and we're going to compute the distortion parameters, the rotation and translation vectors, so we can actually relate how the different frames are to each other, and then we can get the camera matrix. And if you don't know, for example, the focal length of your camera and stuff like that, you will actually get that by using camera calibration as well, because we can take that out from the camera matrix, so we know the focal length of our camera. And then at the end here with camera calibration, we're just using it to remove distortion and get this camera matrix here, the distortion parameters, and also the rotation and translation vectors. So first of all here, we're just going to talk about the camera pinhole model here as well. So we'll go down to the really basics of a camera and how that works, and then we can use that information to actually calibrate our cameras and then get the camera matrix and remove the distortion that we have in our images. So just to go short over here, the camera pinhole model, because we have already been over this one here throughout this tutorial here several times. So if you don't really know different kind of stuff within camera pinhole model and what these different kind of parameters means, make sure to go through those videos as well. Here the tutorial, I also did another tutorial on camera calibration in C++. So if you want to calibrate your camera in C++, definitely go check that video out. But in this video here, we're just going to create a script in Python, so we can just run that script on a number of images, and then we can actually calibrate our camera and get the different kind of parameters that we want. So the pinhole model here is that we actually have the 3D world coordinates up over here, and then we have a point here in the 3D world, and then we can actually project that 3D point down here to the image plane, which is this blue plane here that we can draw here. So we actually get a 2D representation of this 3D point that we have out here in the world coordinates. And then we actually have the optical center here, or the optical center, which is the pinhole here of the camera. And then all the lights here get actually reflected down here. And then the focal length is actually this distance from the pinhole of our camera, or like from the lens to the actual image plane here in our camera. So we can use those informations here to do different kind of stuff within when we're doing camera calibration, and then we can use that information to do a lot of different kind of operations within computer vision. So we can actually like get the focal length here, which is considered as a scaling factor because this is the distance from the pinhole to the actual image plane of our camera. Then we actually have this W here, which is also just a scaling factor for this UV here, which is actually like the projection of our 3D point in the 3D world coordinate system here. And then we have our camera matrix here, where we can actually like have the CX and CY, which is actually here, which is the location of the optical center. But in this example here, we just set that equal to 0 to comma 0. So this will be the location of our optical center. And this is actually like our optical center here of our camera. And then we have this XYZ here, which is this point here in the 3D world coordinate system. So to actually like make the projection from 3D to 2D, we actually like need this camera matrix here, where we have the focal length in the x-axis and the focal length here in the y-axis. And often these two focal lengths here is actually like the same value, but we can get these information here from calibrating our cameras, because we're using 3D points to actually like make projections down on 2D points. And then we get the camera matrix, we can get this distortion parameters, and then we can undistort our images so we don't have the different kind of distortions. So why are we actually like going to use camera calibration? Because as we've already seen, we can have like a camera where we have like this kind of like barrel distortion, or we can also have something called pinhole distortion, and it can be caused by, for example, the lens lens. If we're using in our application a lens where we need like a wide field of view, and we're, for example, using a fisheye camera, then we will have this barrel distortion here, or pinhole distortion if we're using, for example, a fisheye. If you know like what that is, it kind of looks like this here, where we have these curves here at the end or like at the sides here of our image, and that will cause a lot of noise and a lot of like distortion on our images. And if we try to do some operations or like look at these lines here and calculate some different kind of like, for example, disparities when we're going to use stereo vision and stuff like that, we won't get really accurate results, and we can't really use that if we haven't calibrated our cameras. So that's why we're using camera calibration to actually like get more precise results, and we can then also do better operations on our images. So we use camera calibration like basically just to remove the distortion on our camera lens, so we get better frames, and also so actually like get the parameters from our camera if we don't know them beforehand. So we have this pinhole distortion and barrel distortion that we can actually remove from our images when we're using camera calibration. So the method here that we're going to use for camera calibration is something called the SENS Method, and I'll just shortly go over it. I've already went through it in the other tutorial in C++ where we did camera calibration, and we went more in depth with all of this, but I'm just going to explain that we're going to use this SENS method here, and we're just going to estimate like homography to each camera plane. So we're going to take different images of the different kind of like chessboards from different kind of like perspective. We're going to flip and rotate and translate the chessboard around in the image, and then we can actually like estimate the homography to each camera planes of those. And then we'll get a linear solution for the pinhole camera model, as we just went over, that we're using the pinhole camera model. So that's basically what the SENS method is and what we're going to use for camera calibration. And at the last slide here, I'm just going to show you like these results here from the paper of the SENS method. And the most important part here that we're going to like work with in this example here is actually like the last figure down here. So here we're going to find like the relative error here compared to the number of planes that we're going to take. So when we're going to do camera calibration, we might like wonder about like how many different kind of planes and how many different kind of like different frames and like pictures do we actually like have to take, where we rotate our chessboard around, flip them around, and translate it around in the image. And as we can see here at the results, we actually like get here from actually like from 3 to 5 planes here, we actually like get a relatively low error compared to if we're using up to like 15 planes here. Like we won't really get that much improvement by using like 15 planes compared to like only using 3 or 5. So in this example here that I'm going to show you right now in Python, we're actually like going to use five number of planes, and then we're going to calculate the relative error and undistort our image, so we can actually like do operations on that later on. So we're not into the Sublime Text here, where I have this script, a Python script here that we can actually like run to calibrate our cameras on a number of frames that we actually like have stored in the directory. So first of all here, we're just going to look at the images that we're actually like going to do camera calibration on. So first image here I have is the Cali one here, where I just have this camera that we take, and then we can see we have this barrel distortion, or like this Pinhole distortion over here to the left, where we can see the curves of the table here is really curvy out here to the left. So we actually like want to remove that distortion so we can then do operations on those images here. And then for the second image here that we're going to load in, we actually like have rotated and translated our chessboard here around, so we actually like get a number of different kind of views of our chessboard, and then we can use that information to calibrate our cameras. If we look at the third image here, we translate it up, so we have another view here of the chessboard. The fourth one here, we're actually like going to tilt the chessboard, so we'll also get that into perspective. And then the last result here is that we actually like have tilted it at another way again, and we have translated down here at the bottom of our image. And we can see that on all of the images here, we actually like have the same distortion here at the end, because we have this distortion here in our camera lens, which is why we're going to use camera calibration to remove that from our frames that we're doing operations or like different kind of calculations on. So if we go back to the script here again and go through like line by line here the code, and then at the end of the video here we're actually like going to run the code, do camera calibration so we can see what is really going on and when it finds the different kind of corners in the chessboard, and then at the end we're going to see the result when we're going to undistort our image. So first of all here we're going to specify the chessboard size here, so the number of corners that we have in our chessboard, both in the width and the height. So in the width here we actually like have 24 corners that we want to find, and we want 17 corners in the height of our chessboard as well. Then we're going to specify the frame size here, so we have like a 1400 pixel camera like image here that we're going to do camera calibration on. Then we also have a termination criteria here that we set up, and this is just default from OpenCV. So this is just a termination criteria that we're going to use when we're going to find subpixels in our actual like images, so we can find like corners of subpixels, so we actually like get a really exact result or like a really exact position of where the corners are in our chessboard. Then we're going to compare our object points, so we have like our object points in the ideal way that we want them to. So we have this 0.00 and then 1.00, and then it just goes on and on and on until the end. So we just have this set up here and prepare the object points that we can then use later on when we're going to actually like do camera calibration with the OpenCV functions. And this is the same that we do down here, so we just do the exact same thing here. So we actually like have prepared our object points after these two lines of code. Then we're going to have two arrays here where we can store the actual object points that we get from doing our camera calibration, and also the image point here. So our object points is the 3D points in the real world space, so the object points from the actual like chessboard that we're going to get from 3D. So we have our information from the three-dimensional world coordinate space, and then we want to project that down to 2D points in the image plane, and then we actually like have a relation between 2D and 3D by having this camera matrix that I showed you in the slides. Then we're going to use our images here that we're just going to load into these images variable here. So we actually like have all our images stored in this variable, and then we can just have this for loop here where we run through all of the images, do the operations on the images, and then store the result in our object and image points, and then use that to actually like do camera calibration and undistort our images with those results later on. So we're going to use this glob here, which just takes like all the images that is in that folder that has this extension here, PNG. So in the camera calibration folder I have up here to the left, if you can see it, I only have this Python script here of camera calibration, and then I have the 5 images that we just went through with our calibration, which is the PNG images. And I'll just delete results here so they don't load those in as well when we're going to run this Python script. So as I just mentioned, we have all of the images stored in this variable now here, and then we can just have a for loop where we run through all the 5 images that we actually like have in our directory here. First of all, we're just going to print out if we have like an image here that we actually like have an image that we can load in, and then we're going to read in that image here, so we actually like store in this image variable here with OpenCV, so we can then use OpenCV's camera calibration functions to actually like do all of it for us. First of all, here we're going to convert it from BGR. When we load it in, it will be BGR in OpenCV, and then we're going to convert that to a grayscale image. So we're going to operate with grayscale images, because this find chessboard corners function here from OpenCV, it only takes in grayscale images. So when we have our grayscale image here, we can actually like just call this function here from OpenCV, which is find chessboard corners, and it will find all the different kind of corners that we actually like have in our chessboard that we specified up here with the chessboard size. So we will try to find 24 by 17 corners in our chessboard with this find chessboard corners here. We pass also in here the grayscale image that we have. So we find all the chessboard corners that we have in this grayscale image here, and then it will just return all the corners here in this variable, and then we can use that later on to actually like find some sub-pixels of that corner and to get more accurate results, and then later on we can use that to actually like do the camera calibration. So if we actually like found the points here and then we're going to add the object points and the image point after we have been refining them. So if this red here is true, then it was then we know that that we actually like found some chessboard corners with this function up here. So those returns is if it found some chessboard corners and also then the corners that we actually like found in that image. Then we're going to check here if that is true, and if that is true, we're actually like going to add the object points and the image point. So first of all here, we're just going to have this object points here where we actually like have this empty list here at the beginning. Then we're just going to append the object point here that we actually like have up here that we prepared up here in these two lines of code here. And then we can actually like find corners too here where we're actually like just going to go into the sub-pixels of the corners. So if you don't know like how we can find corners in sub-pixels, I also have like a corner detection tutorial where I go over like what is finding corners in sub-pixels and why are we doing it. So if you want to go more into details what some of the different kind of functions here does and also how they do it, then make sure to check the tutorials out throughout this video or like throughout this tutorial here, and then you'll know like everything about like what is going on behind the scenes here and how we can use computer vision and how these different kind of functions here work. So with this video here, we're just going to go over the functions, and then we're going to run the Python script here to actually like do the camera calibration. So here we just take the OpenCV function here, corners, sub-pixels here, so we actually like find the corners in the sub-pixels in this grayscale image here. And then we're going to specify the corners where we want to find like the corners in those sub-pixels where those corners we found were at. And then we're going to specify this criteria or like this termination criteria that we specified up here in the top. And these 11 by 11 and -1 by -1 here is just default parameters for finding these corners sub-pixels here in OpenCV. So we can specify some of these parameters if we needed that for our application. When we have done that here, we're just going to append those corners here in the sub-pixels to those image points here, and then we actually like have both our object points and image point, and we can relate both 3D points to 2D points, and then we can actually like use that relation to get our camera matrix. Then we're just going to draw here and display the corners that we actually like detect on our chessboard, so we can see the images or like the chessboards where we find the corners, do we find all the corners and stuff like that, so we know that we get a good result when we're doing camera calibration. So we're going to use this draw chessboard corners here. We're going to pass in the image where we're going to like draw the actual like chessboard corners, and we specify this im here, which is also like in BKR, so we can see like the color images, because we actually like found them in the grayscale image, but we're going to show the corners that we found in the color images. Then we're going to specify the chessboard size and the corners that we found, and also this red variable here, if that is true, if we actually like found some chessboard corners, or else we won't draw them on our image. Then we're just going to use this imShow function here to actually like show the image, and then we have a wait key here, so we wait for 1 second before we go into the next image. So we run through one image at a time, find the different kind of corners from the chessboard, and then get the object points and image point, append those to the list. Then we wait 1 second, we display it, wait 1 second, and then we go to the next image, and then we'll just run the same process through 5 times, or like number of times, or like the number of planes that we actually like have in our directory. Where in this example here we have 5 images where we have this chessboard that is moved around in the image frame. Then at the end here, when we have been through all the images here, we're just going to destroy all the windows here. Then we can actually like go down and do the actual calibration when we have our object points and our images point. So then we're just going again to use the OpenCV function here, calibrate camera. So all it does here is just, it takes in the object points that we found, the image points here. So now we have actually like object points and image points for all the images that we have processed. We specify the frame size here, and we just specify this none and none here, which is also just default parameters. So all we need to specify is the object points and the frame size and the image points that we just found. And then we use this camera calibration function here from OpenCV, and it will return like if it could calibrate the cameras in this red variable. We're going to get back the camera matrix here, because we can relate the object point to the image point, how we can actually like project 3D points to 2D points, and we use the camera matrix for that. So we can actually like get both the camera matrix, the distortion parameters, our rotation vectors, and also the translation vectors. So now we have all the information that we actually like need from our camera calibration and then we can use these distortion parameters here later on and our camera matrix to actually like undistort our images. But if we want to do camera calibration just to get our camera matrix and also to get our focal length, we can actually like just use this camera calibration here, and now we have all the parameters here that we actually like want. Then we're just going to print out these different kind of variables here when we're going to run the program, so we can see what is going on and how like the camera matrix look like, and also distortion parameters. Then when we have to calibrate our camera, we can go down and use those parameters to undistort our images. And we actually like have two ways to actually undistort our images. We can just use the undistort function from OpenCV, or we can use something called remapping, and they will both return the exact same result. So first of all, here we're just going to load in a new image, and in this example here we're just going to load in the fifth image here from our calibration, so we can see that we actually like remove the distortion that we have in that image. Then we're just going to get the height and the width here of the image, because we want to use that when we call this function here get optimal new camera matrix. So we can actually like do some optimization on our camera matrix, so we get more accurate results by using this function here from OpenCV. We just pass in the camera matrix, the distortion parameters, the width and the height of the frame, and the default parameter, and also the width of the height here again. And then it will return like the new camera matrix that we can then use later on. So when we're going to actually like undistort our images with the undistort function from OpenCV, we just have our like destination here, or like our final image here, which is actually like distorted here, that we will store in this variable. And then we just use OpenCV's function undistort here. It takes in the image that we actually like want to undistort, so it will be this image that we load in up here. And then it takes the camera matrix, the distortion parameters, and a non-default parameter here, and then it also takes in the new camera matrix here that we got from this get optimal new camera matrix function up here. Then we can actually like just set this ROI here equal to the XY and the width of the height. So we're actually like going to crop the image, and then we're just going to crop the image here by using this this slicing here as well. And then when we have cropped our image, then we can actually like inwrite the result here to the directory, so we can actually like see the undistorted image in this example here. So another example, and the last example I'm going to show like the way that we can undistort our image is with something called remapping. And here we get like a map here for the X direction and a map here for the Y direction. And we just use a function from OpenCV that will do everything for us. So when we get these different kind of parameters, we know like how we can use them. We can just run this Python script here with all the OpenCV functions, and it will just return the undistorted image. So we're going to use this init undistorted rectify map here from OpenCV. Again, it just takes the camera matrix, the distortion parameters, the new camera matrix, and the width of the height, just as this this get optimal camera matrix and also the undistort function here from OpenCV does, but it doesn't in some different kind of ways. But you can use both functions here and get nearly this exactly the same result. Then we're going to use this remap function here, where we're going to specify the image, the map here in the X, and the map here in the Y, and then we're just going to specify that we want to use interlinear here, which is just that default parameter again, but we have some different kind of options in OpenCV as well if that doesn't work for our application, but this is just default, so it works like most of the time. And now we actually like have our destination here, or like the final image, just exactly as the same up here. And then again, we're just going to inwrite it out here. We're going to crop the image, and then we're going to inwrite out the result here. And then we can actually like look at both the result here and see if they're the same and what the differences are, but they will be the exact same in this example here. And then at the end here, as we talked about with the SENS method, we can actually like calculate some reproduction error, so we can see like the error from our camera calibration. So when we're using more than 3 planes, then we have a relatively low reproduction error when we're doing camera calibration. So to calculate this, I won't really go into details with this. This is just like a formula how we can actually like calculate it. We're going to use some OpenCV functions with the project points here. So we're actually like going to make a reprojection of the point that we found in the images. So again, we know that we need the object points, we need the rotation vectors and the translation vectors, so we can actually like relate the images or like the object points to each other by using these different kind of rotations and translations that we got from using camera calibration. And then we're just going to calculate the error here with the norm, and then we're just going to calculate the mean error, and then at the end here we're just going to print out the mean error of the reprojection error, so how the different kind of like 2D points and 3D points relate to each other, and what is the error on that. So now we're going to run the program here, and we will load in the images one by one here. It will do the different kind of operations that we just went over. It will calculate the camera matrix, the distortion parameters, and stuff like that, and then we'll print it to the terminal here. So if I just drag this up here, we can actually see that we load in the image here one by one. We will store the results here in the directory, and then we can see here that we actually calibrate our camera here, which is the return value. We get the camera matrix back here, where we have the focal length here in the X direction and the focal length here in the Y direction. And then the two parameters here, or the two values here, is actually the location of our optical center for our camera, when we actually have that in our camera model as I showed you in the slides. Then we will get the different kind of distortion parameters here that we use to actually undistort our image and calibrate our camera. And then we actually have the rotation vectors as well here, and the translation vectors here that we got from calibrating our cameras here as well. And then at the end here, we actually have this reproduction error that we calculated. So we have an error of 0.04 here. So it's a relatively good reproduction error. So we have actually calibrated our camera really good, and we actually have a really low error. So when we're going to do operations and do calculations with our images that we have now calibrated, then we will actually get really exact results, and we can use those images that we have calibrated to do these different kind of operations with very accurate values and results. So if we're just going to look at the results here that we actually got out from doing undistortion on our image, this is when we call the undistortion function here with OpenCV, and we can now see that we actually removed this this curvy distortion that we had over here to the left of the table. So now we can actually use these images or these frames here to do actual and really accurate and precise calculations. If we, for example, had two objects that we wanted to calculate to the distance to, it will be way more accurate than if we had this barrel and pinhole distortion in our image by having this fisheye camera lens effect. So we can see that we have actually removed the distortion here on our image. And if we look at the second result where we used remapping, we can see that we get exactly the same result. We have gotten the same output here. We have removed the edge here. We have a really straight line here off our table, and we have actually removed this barrel and pinhole distortion, so we don't have this curvy edges here out here to the left of our image. And we actually have the exact same thing here to the right, but the table in this example here is more to the left. So the results, the table here or the images here, would actually get affected more over here to the left. But when we actually undistort our images here after we have done camera calibration, we can see that we now have a really nice and straight line here in the image, instead of having this curvy line that we really couldn't use to do operations and calculations with our frames and images with. So that's pretty much it for this video here, guys. I've shown you how we can calibrate our cameras. I talked about a little bit about why we should calibrate our cameras, and also how we did it. I made another video in camera calibration with C++, so if you want to calibrate your cameras with C++, definitely go check that video out. I also get more into details with what camera calibration does under the video, under the functions. Where in this video here, we just kind of use the functions from OpenCV, and we just made this Python script here that we can just load in the images, call this Python script here, and it will do everything for us, and then we can just use the resulting frames here to actually do our operations in our own applications and projects. So thank you guys for watching this video here, and remember to hit the subscribe button and bell notification under the video here, and also like this video here if you like the content and you want more in the future, because it just really helps me and the YouTube channel out in a massive way, and I just really appreciate your support. So I'm currently also doing a deep learning tutorial where we're talking about neural networks, deep learning, how we can create artificial neural networks, convolutional neural networks, how they work under the hood. We're going to actually create neural network from scratch, create a data set that we're going to train our neural network on, and then we're going to do predictions on data that the neural network hasn't seen before, and then make predictions on that. So that's a really nice and cool tutorial that we're going to combine with this computer vision tutorial, so we can see how computer vision and deep learning works together. So if you're interested in that tutorial, I'll link to it up here, or else on the see you next video, guys. Bye for now.